Welcome back. In this lesson, I am going to move into ensemble learning methods introduction. This is really getting to the cutting edge of machine learning technology now, and this is really where it gets extremely exciting because you start winning competition when you start using these ensemble methods. So far, what we talked about has been covering things like logistic regression, linear regression, support vector machine, and the likes. You probably will be asking this question in your mind, say, why don't we just jump straight into these deep end and cutting edge technology and learn from this space? Well, the truth is, a lot of these ensemble methods is built upon a lot of these older technology. And one part that I like to stress is that because I come from a finance background, and the one algorithm that really was the key breakthrough in finance was the modern portfolio theory. The basic ideas of modern portfolio theory is correlation. Correlation matters a lot. When you have perfect correlation between two stocks, you cannot get any diversification benefits. When you have two stocks that is perfectly negatively correlated, in measurement term we call it correlation of -1, then you can create a risk-free asset, meaning you can get returns without taking any risk at all. But in any case, anytime that you have a correlation that's less than 1, you have diversification benefit. The closer it is to -1, the more diversification you're going to get out of your algorithm. Now, expanding on that principle, when you have a correlation of 0 in statistics, this is called independent. Basically, they have no correlation with each other, meaning they are independent of each other. Then you can actually get substantial diversification benefit out of it. So in essence, ensemble methods is built upon these concepts. Now, before we go too deep, let me just start with some basic introduction so that you actually have an idea of what ensemble learning is. Let's start with that. Now, ensemble learning still comes under the supervised learning machine learning algorithms category. It's really a group of predictors or classifiers or regressors, whatever you want to call it, and combined together in different ways. Now, let me just start with the first ensemble methods that I want to cover, and in this sequence as well. The first one I want to cover is called the bootstrap aggregating. Another name for this is called bagging. I have the scikit-learn reference open up for you, so you can actually refer to it at your convenience, but I will go through some of these a bit later in future videos. What is the basic ideas of bagging? It works like this. It's what we call bootstrap sampling as well. In statistics, this is called sampling with replacement. So essentially, if you think of it this way, if I have 100 samples, every time I take 10 out of it. I don't take the whole population or all 100, I only take 10. That is one sample. And then I put that 10 back, and then I draw another 10 out again. That's what you call sampling with replacement. Every time I take a sample, I put those samples back into the whole population again, and I resample. I keep repeating this, and over time, the so-called it will be closer and closer to representation of the population mean and variance. But in this context that we're talking about in terms of machine learning, what we're doing again is also sampling with replacement, and then there are two ways to combine the results. If it's regression, then we combine them by averaging, taking an average. If it's classification based, we combine by voting. What does it mean by voting? I guess you can think of voting as similar to a lot of electoral systems in the world. The party that gets the most vote will win. It's the same basic concepts here. And if I go back to the regression example, whereby you combine by averaging the output, immediately you probably think, why just give it equal weights? If we have 10 samples that we did, why do we need to give it equal weight 1/10? Why don't we do 2 out of 10? Well, you can do that, as it turns out. But for now, let's just stick to the simple example of just taking average of the output, where for classification, we combine them by vote. Now, this can be applied to many classifiers. And basically, what I've already mentioned earlier, it could be your logistic regression, it could be your support vector classifier or machine, it could be your random forest and decision trees, on and on it goes. Or you can even apply it to artificial neural network, ANN, NCART, which we mentioned before, classification and regression tree, etc. Now, a variation to bagging is called pasting. It's actually very, very similar, with one exception, the sampling method. With bagging, the method of sampling is called sampling with replacement, whereas in pasting, it's sampling without replacement. So the basic idea is this: going back to the 10 samples that we have, you can imagine as balls. We take 10 out. Basically, the 10 is our one sample. After we count it, we put it aside. So that means we are left with 90. Now, without replacement, meaning we don't put the 10 back into the population, we do another sample. That's another sample of 10. So that's really pasting or sampling without replacement. So let's look at another one, which is a fairly recent technology, and one that is gaining a lot of popularity and a lot of attention right now, especially over the last few years. The idea of boosting is that you train weak classifiers, and then you add them to a final strong classifier by weighting. Typically, you weight them by accuracy or by vote, as we mentioned earlier. Now, how does this work? Now, once the weak classifier is added, the data are reweighted. How does that work? So let me just give you a walkthrough here, just so that you can actually get a basic idea. So you have training data. You expose your classifier to it. Again, this classifier could be decision tree, it could be logistic regression. You would run your training, and you, of course, will identify those that it classified correctly, and you also identify those that it classified erroneously. So for the misclassified samples, what it does, the next step is that you put more weight when you actually run the next training. So let's just say we have two pools, the correct one and the incorrect one. So next time when we actually do a sample, it could be 50-50, but the followed 50-50 this time. The next time it could be that you are placing 60% of your resources or your focus or your weight on those that you got wrong, and you place 40% attention or weight on those that you classified correctly. So basically, that's what the second point is. The correctly classified samples will lose weight. There are some exceptions here, but we'll leave that for now. The algorithm are forced to learn more from the misclassified samples. So immediately you probably think and relate this into a real life situation whereby, hey, isn't that how human learns? If I'm learning a subject, mathematics for example, if I get it wrong, or get some topics wrong and get it wrong regularly, it means that I haven't learned those topics properly. So what do? I will put more attention on those topics that I have learned wrong and do more practice questions on those. That's essentially what boosting, I should say, essentially what boosting is. You train it once, those that you got wrong, you learn from those mistakes that you made in the past. Therein lies a critical difference between bagging and boosting. Whereas with bagging, you can do multiple sampling at the same time. Boosting is serial. You actually, it learns from the past. So as a result, you have to wait. The second round has to wait until the first round is finished. So naturally, boosting takes a bit longer, and quite a lot longer actually, to train than bagging. So keep that in mind when we actually get to that topic. The next algorithm that I do want to cover and goes into a little bit categories of what you call ensemble learning method I want to actually go into is called stacking. It also goes by another name called stacked generalization. Let's look at a definition from Kaggle. I've also given you a link. I will strongly suggest you to read it because that's really where some of the cutting edge machine learning algorithm that's being developed to win competition. Now, the Kaggle definition of stacking is this. You combine information from multiple predictive models to generate a new model. Oftentimes, the stacked model, which is also called a second level model, will outperform each of the individual models due to its smoothing nature and ability to highlight each base model where it performs best and discredit each base model where it performs poorly. Now, for this reason, stacking is most effective when the base models are significantly different. So how does the step works? So training a learning algorithm to combine the prediction of several other learning algorithms. So step one is you do what you usually do. You expose your training data to the learning algorithm. After that, there's another layer of combiner algorithm. This combiner algorithm, where does the training data comes from? It comes from the predictions of the step one algorithm output. So basically it takes the exhaust or the output or the prediction of the first layer of algo prediction and train on those. Okay, that's pretty much what the combiner algorithm is doing. It's trained using the algo prediction from step one. So essentially, that's really stacking in a nutshell. Now, there are other ensemble learning methods. I'm just going to put them here. I won't go into details. I just want you to be aware of them so that at least you have an awareness that these models exist. I won't be going into these models in the training here. Right. Okay. Well, to understand a little bit more about ensemble methods, this is the last thing that I'll leave with you before we close off this lesson and to go on to the next lesson. Now, because ensemble methods, in the beginning of the lesson I mentioned, it's a combination of multiple predictors. So the important part with ensemble method is that it works best with independent predictors. And when you combine them, you get a much better performing predictors or results. So the key lesson here is it works best when you utilize multiple different algorithms and then you ensemble together or assembly them together to get a much better predictors or model. That's really the basic ideas of ensemble methods. So in the next video, we're going to go into bagging and go into a little bit more depth on bagging. And I'm going to show you some codes on how to actually train it using Python. At least for now, in this lesson, we've covered the different various types of ensemble learning methods, which includes bagging, pasting, boosting, and finally stacking. There's also others that I didn't actually touch on, but those are the key lessons I want you to actually take away in this lesson. I look forward to seeing you in the next video. Thank you for watching.